Okay, example 7. Find parametric equations to represent the line segment from 3, -2 to 4, 5, and then from 4, 5 to 3, -2. So for A, this is something you can do specifically when you have a line, only when you have a line. You can let your x equation equal to x sub 0 plus delta x times t, and your y equation, y of t, will equal to y sub 0 plus delta y times t. Now, x sub 0 is your starting x value. So for A, we want to start at 3, -2, and we want to end at the point 4, 5. So this means this is my x sub 0 and this is my y sub 0. That's what that means. All right. So the delta x just means simply the change in the x's. So the delta x is going to be 4 minus 3, which is 1. And the delta y is going to be the change in the y. So I start here and I end here. It's going to be 5 minus -2, or 7. So my equation, which will represent this line segment, x of t, will be x sub 0, which is 3, plus delta x, which is 1, times t. Y of t will equal to y sub 0, which is -2, plus delta y, which is 7, times t. And so if I were to graph this, we could say, well, let's let t equal to 0. When t is 0, x is 3, y is -2. So we're over here at 1, 2, 3, -2. And then when t is 1, 3 plus 1 is 4. 2 plus 7 is 5. We're at 4, 5. 4, 1, 2, 3, 4, 5. So the direction of movement is from here to here, and this happens when t is 0, and this happens when t is 1. All right, well, if we had to do the same thing, only do it from 4, 5 to 3, 2, we could represent our x of t equation as x sub 0, in this case would be 4, plus the delta x. 3 minus 4 is -1, so this is going to be a negative, times t, -1t. And y of t would be y sub 0, which is 5, plus delta y. In this case, it'd be -2 minus 5, or -7, times t. Graphing this, when t is 0, we're at 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. And when t is 1, we're at 3, -2. 3, -2. 3, -2. Here. So this is it's the same line segment that we've described, only the direction is down instead of up. But you can only do this method when you have lines. All right. Example 8 says, find the parametric equations for the path of a particle that moves along a circle. X squared plus y minus 1 squared is equal to 4 in the manner described. And so there's 3 different ways we have to describe its movement. So this is my equation, x squared plus y minus 1 squared is equal to 4. If I divide both sides of this equation by 4, I get x squared over 4, or x over 2 squared, plus y minus 1 over 2 squared is equal to 1. And if I remember my Pythagorean identity, sine squared plus cosine squared is 1, then I can write this as sine and cosine. Now I can let x over 2 be sine squared of t, or cosine squared of t. I'm going to choose to let this be cosine squared of t. X over 2 is equal to cosine squared, is equal to cosine of t, because x over 2 squared would be cosine squared of t, So I can solve for x. X is going to be 2 cosine of t. I can let y minus 1 over 2 equal to the sine of t, and I can solve for y. Y is going to equal to 2 sine of t plus 1. Now, alternatively, we could have let x over 2 equal to the sine of t. That would be fine. And y minus 1 over 2 equal to the cosine of t. That is still a true statement, and that would be fine. If we did it that way, we would just have to adjust the parameters, what we let t be when we describe the movement that we have to describe. So that's what would change there. As it is, I'm just going to proceed this way. So what we have to describe in part A is once around the circle in a clockwise direction starting at 2, 1. So for these equations, let's see if these will work. Let's let t equal to 0, t equals 2 pi over 2, t equals 2 pi, t equals to 3 pi over 2, and t equals to 2 pi. All right. Once around means I'm going to go through one period for these functions, 0 to 2 pi. That's what that means, the parameter. So what is x when t is 0? And what is y when t is 0? Let's see what we get here. Okay, when t is 0, this is 2 times 1, or 2. When t is 0, this is 2 times 0, which is 0 plus 1. This is at 2, 1. Okay, so that's one thing we needed. Start at 2, 1. That worked. Let's see. Pi over 2 gives us cosine of pi over 2 is 0. Times 2, we get a 0. 2 sine of pi over 2 is 2 times 1 plus 1. We're at 0, 3. So let's look and see what's happening here. We're at 2, 1. I'm sorry, that's not 2, 1. That's 2, 0. We're at 2, 1. Okay. And then we're at 0, 3. So we went from here to here. Okay. That is a counterclockwise movement, and they wanted clockwise. So I have to change something. So let me change. Instead of going up, I want to go down first. So what I'm going to do to change is put a negative in front of my y. Let's see what happens there. So this is the change that I made right here. So I put a negative in front of that. So let's see. What else might change? When I put in 0, 2 times cosine of 0 is 2. When I put in 1, negative 2 times the sine of 0 is still 0 plus 1. I still get a 1 there. When I put in pi over 2, 2 times the cosine of pi over 2 is still 0. When I put in pi over 2, this is a 1 times the negative 2. Negative 2 plus 1 is a negative 1. What's happening? I start at 2, 1. That's where I needed to start. And then I went down to 0, negative 1. Right here. So I went down this way. That is clockwise. So that's working out. Let's keep going. The cosine of pi is negative 1. We're at negative 2. The sine of pi is 0. We're at negative 2, 1. So now we're over here at negative 2, 1. All right. And then at 3 pi over 2, we're at 0. This is going to be a positive 2 plus 1. We're at 0, 3. Okay. And then at 2 pi, we're at 2, 1. Back around. So what happened here? We needed to go once around the circle. That means t is going to be limited between 0 and 2 pi. That's going to be one circle around. So this is what we had to put on here for part A. This is t, and we had to put that negative on the y. These are the equations that worked for A. All right, let's look at B. 3 times around counterclockwise, starting at 2, 1. All right. Well, we had it going counterclockwise before we put the negative on there. So these equations have it going counterclockwise. And they also started at 2, 1. Just to check, we can go ahead and plug these in. T is pi over 2. t is 3 pi over 2, pi, sorry. T is 3 pi over 2, t is 2 pi. All right. What happens there? For x and y, this is going to give me a 2. This is going to give me a 1. We start at 2, 1. Okay, that is correct. Okay. Pi over 2, this is going to give me 0. This is going to give me 3. 3 pi, this is pi, sorry. This is pi. At pi, cosine is -1, so that's a -2. And that is going to be 1. 3 pi over 2, this is 0. This is going to be -2 plus 1, -1. 2 pi is 2. And that is going to be 1. All right, what does this one look like? We start at 2, 1. Here, okay. Then we go up to 0, 3. Then we go to -2, 1. And then we go down to 0, -1. Then we're back to 2, 1. So we're here, 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 here. So we got the counterclockwise motion going. We started at 2, 1, right? So that's all good. The only thing is 3 times. 1 period is 2 pi. So we need 3 of them. We're going to have it go to 6 pi. So these are the restrictions that we'll put on our parameter t. So these are the equations that we needed for part B, and this is the restriction that we needed. And to indicate 3 times around, this is the second time around, this is the third. I'll put 3 arrows here to indicate it happened 3 times. Okay, now part C, halfway around, only halfway around, and counterclockwise, starting at 0, 3. So the counterclockwise movement is happening when we have these equations, all right? Halfway around would require that we cut the period in half. We're only going to move pi units, but we have to start at 0, 3. So we need to use these same equations. X is 2 cosine of t. Y is 2 sine of t plus 1. This got us the counterclockwise movement. But we want to start at 0, 3. One way to do that is to say, let's start at pi over 2. And if we only go pi units, pi over 2 plus pi is 3 pi over 2. So we can restrict our t from pi over 2 to 3 pi over 2. And what that did was we only went halfway around, and we started at 0, 3. So let's make sure. Oops, that's not what I meant to do. I'm so used to drawing the unit circle, I do that almost automatically. Okay, so if we start at pi over 2. All right, at pi over 2, this is x is going to be 0. And at pi over 2, that's 2 times 1 plus 1. We're at 0, 3. We are starting at 0, 3. Good. And then at pi would be the next thing. 2 times -1 is -2. At pi, this is 0 plus 1. We're at -2, 1. -2, 1. Right? Okay. And then 3 pi over 2 would give us 2 times -1, -2. Is that right? No. 3 pi over 2, that's 0. We're at 0. 2 times -1 is -2 plus 1 is -1. We're down here at -1. Okay. All right, and so we only went halfway around the circle, and how we achieved that was the same equations, but we had to start at 0, 3, but we achieved that by changing our start and stop for the t. All right, cool. This is number 9. It says a projectile is fired with an initial velocity v sub 0 of 500 meters per second at an angle alpha above the horizontal, and air resistance is assumed to be negligible. Then its position after t seconds is given by the parametric equations. X of t is v sub 0 cosine alpha times t. y of t is v sub 0 sine alpha t minus 1/2 gt squared, where g is the acceleration due to gravity, or 9.8 meters per second squared. So let's describe our equations. X of t is equal to v naught, or 500, times the cosine of 30 degrees times t. And the cosine of 30 degrees is square root of 3 over 2. So it's 500, or 250 times the square root of 3 times t. All right. Y of t is equal to v naught, 500, sine of 30 times t minus 1/2 g, which is 9.8 times t squared. All right. So let's simplify this a bit. The sine of 30 is 1/2. So 1/2 times 500 is 250. So this is going to be y of t is 250t minus 4.9 t squared. That's what y of t is. All right. Those are our equations. Now it says if a gun is fired with alpha is 30, v sub naught is 500 meters per second, when will the bullet hit the ground? So they want to know when it's going to hit the ground. Well, y of t is our height equation. And so when something's on the ground, the height is 0. So all we have to do is set this equal to 0 to figure that out. So let's set this equal to 0 and solve. We can factor out a t here. We're left with 250 minus 4.9 times t. When we solve for t, we get t is 0. That's when initially when the bullet's fired. And then the second time, 250 divided by 4.9, gives us when t is 51 seconds. That's when. So that's part A, when the time is 51 seconds. And then it says how far from where it's fired will it hit the ground? Horizontally, how far did it move? Well, all we do to figure out part B is we say, well, what is x of 51 seconds? So what is 250 times the square root of 3 times 51 gives us 22,883 feet. That's how far it moved. Okay, wait, feet, meters. I've got everything kind of messed up here. This is meters. That's how far it moved. Okay, now, C says, what is the maximum height reached by the bullet? So, we can use some calculus here. Let's take the derivative of the height equation. So, y prime of t will be 250 minus 9.8 t. We can solve for the critical value, set that equal to 0 and solve, and we'll find that t is 25.5. We can do a little test, 25.5, and we can do some test points and find that, maybe put in 24 and 26. What we'll find is that the derivative is negative on this side. It's positive on this side, meaning that it's increasing, and it's negative on this side, meaning that it's decreasing when we plug in 26, which shows that there's a max at this critical value, or the maximum height's going to occur there. So, what is the maximum height? Evaluate the function y at 25.5. All right. That's 250 times 25.5 minus 4.9 times 25.5 squared. And I get that the maximum height reached is approximately 3,189 meters. So there's an application with our parametric equations.